Hello everyone. My name is Akhil. I'm a PhD scholar from IIT Madras. We'll be having this weekly live sessions for the course Basics of Material Engineering, where we solve the problems every week from Tuesday. So for this week, we'll be focusing on again is one or two questions on failure theories, and then stress concentrations and extra. Yeah. So today we have two more questions on the brittle fracture. Why is this not updated? Okay, let me share the screen again. It's not updating. Yeah. So today's first question is failure of brittle materials using modified Moore stress theory. And we were given one axial stress and one shear stress. And the other sigma y is 0. So what is the first thing we should do from the stress tensor? We should estimate the principal stresses, right? So when it's in 2D, the stresses are only in 2D. For principal stresses, we can directly estimate them through the formula sigma x plus sigma y by 2 plus or minus root over sigma x minus sigma y by 2 whole square plus tau x y square, right? So if we substitute these numbers here, so minus 100 plus 0 by 2 plus or minus root over minus 100 by 2 whole square plus tau x y whole square 75. So minus 50 plus or minus root over 50 square plus 75 square. So can anyone tell me what should be this? So here the principal stresses would be, so sigma 1 we can take it as minus 50 and plus 90.14, so that would be positive. So we can take sigma 1 to be positive, and then sigma 2, sigma 3. So in general, we will have a three-dimensional state. So we have the three principal stresses, and because the actual stress is only two-dimensional, one of the principles would be 0. And because we will be getting one negative, so and the general order which we use is sigma 1 greater than sigma 2 greater than sigma 3. So we will take sigma 2 be 0, and then sigma 3 to be minus 50 minus 90.14, so minus 140.14. Okay. So now we have the principal stresses. So for modified Moore stress theory for brittle materials, there is a way to get the effective stress, sigma effective. So is defined as the maximum of C1, C2, C3, sigma 1, sigma 2, sigma 3. So how do we estimate the C1, C2, C3? We'll see now. So C1 is half into sigma 1 minus sigma 2. So this straight lines means absolute value you need to take plus 2 into SUT minus into sigma 1 plus sigma 2. So this is C1. Similarly, C2 would be and C3 would be okay. So now for we know what is sigma 1, sigma 2, sigma 3. So using those, let's estimate C1. So half into sigma 1 minus sigma 2. So here sigma 1 minus sigma 2 would be 41, because sigma 2 is 0, it should be 40.14 plus 2 into, we are given SUT as 350 and SUC as 550 by, let's write directly, 550 into sigma 1 plus sigma 2. So here sigma 2 is 0, so sigma 1 is this only. So this becomes half into 40.14 plus okay. So 350 into 700 minus 550. So top is 150 and here we have a minus into 40.14. So this will finally will give us 14.6. So you can do these calculations, and then C2 similarly if we can estimate, I mean I won't be doing every calculation, I'll directly write the values. 89.2 and then C3 would be 103.8. Okay. Now we have C1, C2, C3, sigma 1, sigma 2, sigma 3. So what is the maximum value? Sigma effective is maximum C1, C2, C3, sigma 1, sigma 2, sigma 3. So maximum 14.6, 89.2, 103.8, and sigma 1 is 40.14, 0 minus 140.14, right? Yeah. So what is the maximum value in all this? So this one C3, so 103.8. So now the factor of safety would be SUT by effective stress. Okay. So this is the modified Mohr stress theory using the Dowling's effective stress formulation. So 350 by 103.8. So that would give us 3.37. Okay. So there is something called modified Mohr equation also. So if we use that, in that case, the factor of safety you can write it as SUT minus of sigma 1 plus sigma 3 by SUC. Okay. So if you use that, then in that case it would be sigma 1 by SUT. Sigma 1 is we got 40.14 by SUT is 350 minus sigma 1 plus sigma 3. So we have 40.14 and minus 140.14. So this would be minus 100 by SUC, which is 550. So 40.14 by 350 plus 100 by 550. So this would also give us same as the earlier 3.37. So is this clear? Suresh? Modified Mohr stress using the effective stress formulation developed by Dowling. Yeah. Second one is directly modified Mohr equation. So here this actually turns out to be the case where C3 is maximum. Okay. So the case where here the maximum turns out to be C3, in that case alone, if you do directly this way, you will get the same answer. But if that is not happening, then you won't get the same answer. Okay. So whenever if you are asked modified Mohr stress theory, please use this one. This will be applicable for every case. Yeah. First one. Everywhere. Only whenever C3 is maximum. So only in that case. So that is a special case. So in general, if you are asked modified Mohr stress theory, you can use this only. Maximum of C1, C2, C3, sigma 1, sigma 2, sigma 3. Okay. Yeah. So even if the case where the type 2 is true, this maximum if you use, it will come out automatically. So if you use this, you will get every case. Okay. Yeah. So that is the first question. So if you are given a 2D stress thing, and how do you estimate for brittle materials using modified Moore stress theory? So yeah, now let's see one more question. So this question is exactly in your assignment, but here we have changed the numbers. So you can see how am I solving, because the force is actually on an extra arm, not on the bar, but we need to estimate for the bar. Okay. Yeah. So here we have 6 kilonewtons force acting at this ending of the arm, and then we are given the length and A, and again tensile, ultimate tensile strength and ultimate compressive tensile strength is also given, compressive strength, and again we have to use modified Moore. Okay. So first we need to actually estimate the stresses in the bar. So this force F actually directly gets carried to the bar. So if you take the bar beam only, so this force F will, if you take the arm, here F is acting upon this, and here it is fixed. So if you draw the free body diagram of this arm alone, this F is balanced by F provided by the bar. So there will be one more F to balance the forces. And if you look from this point, there is a torque F into A on this. So that is also is balanced by the bar itself. Okay. So this is for arm. Now, so at this point on the bar also we will be having this reaction forces F and the moment Fa, shear stress. Basically the torque here becomes uh, torque like this. So these two you need to take. Okay. Now this is the bar which we need to study. Now because of this force F, the bar would bend, right? Bending moment. So this is an exaggerated thing. So there would be a bending stress, and that would be along the axial direction, along the axis. Now this bending stress, because if you see the top part is expanding and the bottom part contracts because of this force. So the if you look at the stress through the thickness, so at this point you will have a tensile, and at this point you will have a compressive. So at the top side you will have tensile stress, and at the bottom side you will have compressive stress due to the bending. Now we look at this point A where it's tensile stress. So to get the tensile stress, in this case, in the for a momentum, the formula directly is my by I. So it will be maximum at outer circumference. So this would be mr by I. Okay. So m into r is d by 2, and I is pi d power 4 by 64. Okay. So this would actually boil down to 32 m by pi dq. Okay. So this would be the axial stress developed due to a momentum acting upon one end. So here m is what? F into length L. Okay. So in this case 32 F L by pi dq. Now because of the rotational torque created by this force F, there will be a shear stress generating. So if you look at the circle, so there will be a shear stress tau. So that would come from, if there is the torque is T, tau R by J, and J being pi d power 4 by 32. Okay. So this would eventually boil down to 16T by pi dq. But here this torque is equal to F into A, right? So If you write tau, 16 into F into A by A is the arm length, yeah. So F into A by pi dq. So if you look at this point A, is my screen lost? Are you guys able to see my screen? Okay. I think there is some problem in the sharing. Now, so is it clear till how we got the shear stress tau? So if you look at point A, so there you have shear stress tau and the axial bending stress. Okay, so that would be into the paper. So if you look at that point A in a different way, then this would be sigma A, and then tau would be again out of the paper. So if you, okay, now at that point we have sigma x is 32 f L by pi dq, and then tau xy as 16 fa by pi dq. Okay, so if you plug in the numbers, what were the numbers which I have given? Yeah, so I have given force as 6 kilonewtons, L is 200 mm, A is 200 mm, and dia is 50 mm. Okay, so let's plug in these numbers. So 32 into 4 6 kilonewtons, L is 200 mm, so 0.2 by D is 50 mm, right? So 0.05. Okay, so now torque, this would be 16 into F is 6000 kilonewtons, so 6000 newtons, into A is again 0.2 by pi into dq, so 0.05 whole cube. So D is 15. Yeah. So if you substitute these, what you will get? So let me just plug in these numbers and then see. Okay, so we have 60 kilonewtons, so 6 kilonewtons, and then A is 200 mm and L is 200 mm, D is 15. Okay, so this would give us, yeah. So if you plug all these numbers in, I am directly writing the answer in megapascals. So this would come around 97.78, and this would come around 48.8. Okay. Now once you have the sigma x and tau xy, you have to follow the procedure which we discussed in the earlier question, exact procedure. So from this we will get again sigma 1, sigma 2 is sigma x plus sigma y by 2 plus or minus root over sigma x minus sigma y by 2 whole square plus tau xy square. Okay, this would give sigma 1 as 118.04, and again here one of the stresses becomes negative, one of the principal stresses, so we will take sigma 2 as 0 and sigma 3 to be minus 20.25. Okay, from this again we have to estimate c1, c2, c3 like we have seen in earlier question. So those will come out to be 80.43, 6.45 and 86.88. No. Yes. Yes, Suresh. Yeah, I'll repeat it. Yeah. Yes. Can we discuss this at the ending? No, in that question only the bending stress, the maximum bending stress. If the question is first question you are asking, uh, yeah, shear stress only the maximum shear stress. That's it. Yeah. So now in this case, second. Yeah. So sigma 1 2 sigma x plus here sigma y is sigma axial. So there is no actual shear stress in y direction. Right? There are no forces in y. So sigma y is actually 0. Okay. Yeah. So with that we will get sigma 1 and sigma 2. So which will come as so those are done. So 118.04 plus and minus 20.25. So by convention we will take sigma 1 as 118.04, sigma 2 as 0 and sigma 3 as minus 20.25 because our convention is this, right? Okay. Now for these again you need to estimate C1, C2 and C3 like we have seen earlier in terms of this formula. Okay. Half into sigma 1 minus sigma 2 plus 2 into SUT minus SUC by minus SUC and sigma 1 plus sigma 2. So if you do this, then you would get, I have actually solved this in MATLAB, so I don't have to do the calculations here. 4.5 and 96.3. Okay. So again, now we need to again look at what is the maximum of for sigma effective. So maximum of C1, C2, C3, sigma 1, sigma 2, sigma 3. So maximum of C1 is 91.8, 4.5, 96.3, 118.04, 0 and minus 20.24. So which is the maximum? This one, right? So sigma effective is 118.04 and factor of safety is SUT by sigma effective. So I have given SUT as 200. So 200 by 118.04 which would give us 1.69. Okay. Is this clear everyone? So if you are in the first question, we are already given the stress profile, stress tensor. In this question, we need to first estimate the stress tensor and then estimate the principal stresses and then estimate C1, C2, C3, sigma 1 and then see the maximum and then the factor of safety. Okay. So is this clear or does anyone have any doubt in this question? So your assignment is exactly very close, but the numbers are different. I think you should be able to do it now. So yeah. So question 3. Uh, we have a circular rod type of sample and then which is we are doing tensile test, so there is a T actually on both ends. Now we did this till the failure, okay, and at the failure this is for one sample 1 we got sample A and this is how the failure is for sample B. Now based on this, can you tell which material is what type, whether it is brittle or whether it is ductile? Vinod, your side. Yeah, anyone can answer. Okay. So can you explain me the reasoning? Yes, yes, that is the correct answer. So can yes. So the actual answer is B is ductile and A is brittle. Okay. So the reason we will see now. So we are actually discussed the maximum normal stress theory and maximum shear stress theory, right? And do you know which to apply to what? What type of material systems? So maximum shear stress theory is applicable for ductile materials and maximum normal stress theory is applicable for brittle materials. Okay. So the reason, so maximum normal stress theory is applicable for brittle materials and maximum shear stress theory is applicable for ductile materials. That's what experimentally we have understood. Okay. And if maximum shear stress theory is applicable for ductile materials, so what does that mean? It's actually failing when shear stress crosses some barrier and your test is pure tensile test. So when you are doing pure tensile test, so sigma x is some value and then sigma y is 0 and then tau xy is 0. Okay. So this will be in one plane. Now this is pure tensile test. Now because the other two are 0, if you now for this case, what will be the principal stresses? So sigma x by 2 plus or minus root over sigma x by 2 whole square plus tau xy whole square, right? Tau xy is 0. So sigma x by 2 plus or minus, this would give, so sigma x and 0. These are the principal stresses. But what will be the tau maximum? So okay. So here in zero plane, in the zero, like in the plane of the sample, so here sigma x would be there. So that will be the plane in which normal stress would be maximum. But what will be the plane in which shear stress would be the maximum? So that would be a 45-degree plane. So, so if you are doing an uniaxial tension, the plane in which shear normal stresses would be maximum is the plane at perpendicular to the axial loading direction. So this plane, I will put it in green only. Yeah, this plane. And shear would be maximum in 45 degrees plane. Okay. Now uh, we have seen one sample is failing when in the plane perpendicular to the axis. So it is failed when sigma x has crossed some barrier. So that means it is failing with normal stress theory behavior. So it is a brittle material. Okay. But in the sample B is failing at 45 degrees plane. So it failed when maximum shear stress has crossed some barrier. Okay. So that means maximum shear stress theory. So that is why it is ductile material. So is that clear? So if you do similarly pure torsion, you would get a different things. So that I am leaving for you to work upon. Okay, this is how you can characterize the material. If you just do a simple tensile test, and based on how the failure is, you can tell easily whether it is brittle kind of material or ductile kind of material. Okay. No, it's an assignment question, right? So yeah, I think it's an assignment question. Yeah. So I want to give that. But similarly, you should see the maximum normal stress and the maximum shear stress and the planes in which they occur in pure torsion. And based on the failure, you can characterize. Okay, Suresh? So now we are in the concentration factor type of questions. So because of that stepped shaft, now this stepped shaft is subjected to a torque on both sides, and we are supposed to estimate the maximum stress in the entire shaft. So you are given the dimensions of the larger dia and smaller dia and this radius and the torque applied also. So as we have seen earlier, shear stress for torque applied case is what? Can anyone tell me the formula if they remember? Yes, exactly. So if you see here, we have capital D which is greater than smaller d. Which do you think will actually have maximum shear stress? The larger dia part or smaller dia part? Yeah. So now we know that here this d we actually should use the smaller dia. Okay. Yeah. Now because of this notch or step, we will have some more stress than this value, higher stress than this value. So that factor is this Kt, stress concentration factor. So now we are supposed to estimate that from this chart. So this chart here on the x-axis we have R by D, and each curve corresponds to each d by d value. Okay. So first let's see what is R by D here. R by D is equal to 5 by 50. So 1 by 10 equal to 0.1, and then d by t is equal to 100 by 50. So equal to 2. So we should look at R by D 0.1. So we got R by D is equal to 0.1, and then d by d is equal to 2. Okay. So R by D 0.1. So this line, and d by d equal to 2. So this point. Okay. So this would be 1.5. So this would be what we want is 1.5. So now the actual maximum shear stress that can occur in the material is Kt into the tau value which you get. So Kt into 16T by pi dq. Okay, so Kt we got as 1.45. Okay, and then 16. So torque is given as 150 Newton meter. So you should be very careful doing the dimensions. Okay, so everything we are using SI units. So you should convert every time. So 50 mm, so 0.05 whole cube. So this would give us tau max. For the final thing, I'll just write the answer also. So let me plug in my 1.45 into 16 into 115. Yeah, let me also calculate. 0.05 whole cube. What was the answer you got? No, I'm getting a different number. Can someone else also check? So 1.45 into 16 into torque is 150 Newton meters by pi d cube. So I'm getting around 8.87 actually, MPa. So Akash, please check your calculations once more. So yeah, so this is how you can estimate in a stepped shaft the maximum stress. in the case where it's torque. Okay. Now we'll have one more question where we need to estimate the bending maximum. Yeah, 8.87. In your assignment, the numbers are different, so anyway, you need to solve again. But this is how you should solve. Okay. Yeah. Okay. Okay. Thank you, Suresh. So next question. Yeah. Here, a similar stepped shaft, but here we have single step. Here we have two steps. Okay. And we were given again small d, capital D, the radius, and momentum. Okay. So for the moment, what should be the shear axial stress from earlier? So what did we get? 32 m by pi d cube, right? So similar to earlier answer, maximum would be again kt into this sigma a, and this maximum will occur in the smaller dia region again. So this d should be the smaller dia. So kt into 32 m by pi d cube. So again d by d is 2 and r by d is 0.1. So let's check for that point. So r by d 0.1 lies here and d by d equal to 2. So the last line is d by d equal to infinity. So the next one is 2. So that is this line, second one, and it matches here. Okay. So that would actually, this would be 1.9. So this would be 1.95. Clear? So kt equal to 1.95 into 32. M is given as 100 Newton meters by pi d cube. So 0.05 whole cube. So you would actually get your answers in pascals, but I'm directly writing it in MPa. Okay. So is this clear? Now any type of questions you should be able to solve. Okay. So in the cases where both are there, m and tau, you should use individual concentration factors to get the possible tau max and possible sigma max. Okay. Possible shear stress maximum and possible axial stress maximum at a point. And then you can do the safety factors and rest of the analysis if you are asked. Here we are only asked the maximum stress, so this is how you should do. Is this clear? So let's move on to the next question. So we have a very large plate with a circular hole in it, and then there is a stress at the endings. Okay. Now sigma infinity is given. We are supposed to find the stress at point A. So in your textbook, you will actually get a direct formula for the kt in this case as 1 plus 2 into a by c. So this formula is applicable for a case where it's like this elliptical, a being this and c being this. Okay. Because here a and c are same, kt would be 3. And therefore sigma maximum would be just kt into sigma infinity. So 3 into 400, 1200. So is this clear? Yeah, yeah. So I'll give you a better figure from the book. Okay, so that is how you can get in this simple cases just kt equal to 1 plus 2a base. Now let's move on to the next question. So here we have a large plate, steel alloy, and it has a fracture toughness. During service at a stress of 300 MPa, fracture occurred at a crack length of 20 mm. But if crack length is decreased to 10 mm, what will be the stress at which failure occurs? Okay. So there is something called stress intensity factor and all. So this is using that because of the crack and then corresponding fractures. Okay. So the stress intensity factor K or this fracture toughness you can estimate as sigma beta into root pi a. Okay. So this sigma is the stress which are applying and pi a. So here a corresponds to, yeah. So 2a is the total crack length actually, and a is half of the crack length, and this is b. Okay. So here because we were given large plate, that means a is much less than b. So large plate, yeah. So if a is much less than b, b actually equals 1. But in this case, let's see, because we are already given 20 mm crack length and 300 MPa stress, and fracture toughness was also given. So beta we can actually estimate. Okay. So let's see, k equal to, k is given as 75 beta, and sigma is given as 300 into root over pi. So fracture crack, total crack length 20 mm, so 10 mm. So 0.010. Okay. So if you solve for this, you will actually get beta. But we are not asked that actually. We are asked if the crack length is decreased to 10 mm, what will be the stress at which it fails? So to just get that, so we have K. Because the material is same, this K won't change, right? So this K is equal to beta sigma root pi A1 should be same as beta sigma 2 root pi A2. Okay. So if you take the ratios of this, 1 is equal to, so sigma 1 root A1 by sigma 2 root A2. So A is the half of the crack length. So in this case, we want sigma 2 is equal to sigma 1 root over A1 by A2. So we are doing equation 1 by equation 2. So K and K, it will be 1, right? We are doing equation 1 divided by equation 2. Okay. So sigma 2 would be root over. So A1 is half of 20. So 10. And A2 is half of 10. So 5 mm. So this would be actually equal to 300 root 2. So you would get 424.25. Same as, yeah, similar but different numbers. So there, that is how it is defined. That is how this formula is defined. Yeah. So if this is the crack, so you take half of that as A, define it as A. Okay. Yeah. So I hope this is also clear. Now let's move on to next question. Yeah. So here for 300 root 2, so 424. So 300 into square root of 2, yeah, 424.26. So I think you have a similar question in your book also. So in that you are actually which was yeah, you have a similar question. So there also crack length is changed. You are supposed to find the new nominal stress at which it fails. Yeah. Okay. Now this question here what we have is, so this is actually a crack which is expanding because of the load P you are applying on both ends. So you have a material like this. Now you are applying force on my fingertips and then increasing the crack. Okay. So this crack increase rate is actually defined in terms of energy release rate. So now we are asked, we are given the crack length, specimen height and everything, and we are supposed to estimate the energy release rate. Okay. So Sar actually discussed this in the classes. You can actually refer to that for the exact derivations of the formulas. So here we will actually directly apply the formulas and see. So G, energy release rate G, if in this case where load P is applied, so actually you can write it as B being the width, okay, into dC by dA. So C is the compliance, which is the deflection for ratio of deflection and the applied load P. Okay. So now this C, first we need, our job is to estimate C. So if you look at this part, which is delta by 2, and this length being A, crack length. So for that case, so this is similar to a cantilever beam, right? So this is deflection F and load P applied, and this is length A. Okay. So in that case, what will be the deflection? Does anyone remember the formula? So load into L length here A by 3 EI. So for a cantilever beam, this is the deflection. Now our total deflection, the gap between two parts is 2 into delta. 2 into this deflection. So delta is actually 2PAQ by 3EA. Okay. Now C is delta by P. So this would make it C is equal to 2AQ by 3EA. Okay. Now to get G, first we want DC by D. So it would be 3 to the 6 A square by 3E. Okay. Now the total energy release rate is P square by 2B into dC by dA, which is 6A square by 3EA. So 3 to 6 gets cancelled. So P square A square by PEI. So what is I in this case? So I is, so this 2H is actually for the total. So this would be H, this would be H. So for a single cantilever beam, it is B and H. So I would be BH cube by 12. So total energy release rate would be 12 P square A square by E into B square H cube. Okay. So this question, even though in this assignment it's not there, it could be asked in your exams because it is there in the previous year assignments. Okay. So this is how you can get the energy release rate. So if you actually put in all the numbers in this case, G is equal to 12 into P. Here we have given P as 9 kilonewtons. So 9,000 whole square into A, crack length as 20 mm. So 0.02 whole square by elastic modulus 200 GP. So 200 into 10 power 9 into B square. So B is given as 10 mm. So 0.01 whole square into h cube. Here the total thickness is height is 30 mm. So h is actually 15 mm. Okay. So 0.015 whole cube. So you can plug in all the numbers. So let me plug in 12 into 9000 square into 0.02 square by 209 into 0.01 square into 0.015 cube. So 5.76 into 10 power 3. So this would be in, so everything we have used SI units. So energy release rate is joule per meter square. Okay. Hello. Yes. Ah, yeah. Then you should. It will be very different. Then this won't be applicable. Energy release rate. This entire formulation is depends on the mode. I am not exactly sure, but you have to derive from the energies. Okay, you have to first get the pi as Sar showed in the calculations in the lecture. First, you should get pi, and from that pi, you can estimate this g and all. Okay, yeah. So I'm not exactly sure what will change because I haven't solved for mode 3, but that is what. Yeah. So yeah. So next we have a similar question, but instead of load P, now we have momentum at each n. Okay. Here, what would be C? So when it is moments, now you need to look at the angle. Okay. So let's say this angle is would be, so here I am denoting the total angle between these two extremities as beta. So here C would be beta by m, but beta by 2 is actually, you can, for a cantilever beam you have a direct formula, so, which is ma by ei. So in this case C would become 2a by ei, which would make it dc by da to be 2 by ei. Okay. Now similar to before, here energy release rate in terms of moment would come out to be, so m square by 2b into 2 by ei. So m square by b ei. So m square by b again is b h cube by 12. So 12 m square by b into b square h cube. Okay. So if you plug in the numbers, you will get the answer. But yeah, this is it. How you can estimate the energy release rates? If you have any doubts, we can discuss. But that is it for today. So is this clear for everyone? Okay. Thank you everyone. Thank you for the session. So I'll upload this mostly tomorrow by tomorrow. That's it. Thank you. If you have any questions, you can ask in the discussion forum also. I'll reply as soon as I. Okay. This document at least I'll upload tonight only in an hour. The video will take some time. Yeah. Okay. Thank you.